Good afternoon, everybody, and welcome. I think we've hit the sweet spot here. It's a full house, and the fire department hasn't been here yet, so we're in good shape. A few standing, but this is a great turnout for a great speaker that we have today. My name's Rich Corsi. For those of you who don't know me, it's my pleasure and honor to serve as the Dean of the UC Davis College of Engineering and to welcome all of you to the first event from our new Artificial Intelligence Center in Engineering presentation on AI and Society. A conversation with distinguished AI speaker and Microsoft Chief Scientific Officer, Eric Horvitz. Eric and I were just geeking out about air cleaners outside. So he doesn't just do AI things at Microsoft. He actually knows a lot about portable air cleaners. So before we begin, let us take a moment to acknowledge the land on which we're gathered. For thousands of years, this land at UC Davis has been the home of Patwin people. Today, there are 3 federally recognized Patwin tribes: the Kachil-Dihi Band of Wintun Indians of the Calusa Indian Community, Quetzal-Dihi Wintun Nation, and the Yocha-Dihi Wintun Nation. The Patwin people have remained committed to the stewardship of this land over many centuries. It's been cherished and protected as elders have instructed the young through generations. We're honored and grateful to be here today on their traditional lands. Once again, we're so pleased to host you today to learn from our inaugural AI speaker, Microsoft Chief Scientific Officer Eric Horvitz. As we all know, AI is a rapidly evolving technology. It's accessible to many. AI has shown great potential for advancing our research in engineering and in computer science. Aside from its impact on research, AI has likely influenced all of our lives, from what we see on our social media feeds to search results, and of course, a lot more. With several AI experts in our College of Engineering, AI was identified as a cross-cutting theme of our strategic research vision when it was launched in 2022. My goodness, it's been 3 years already, right? In 2022. AI is being leveraged across our 4 research impact areas, which include revolutionizing energy systems, strengthening climate resilience, transforming mobility, and advancing human health. This past October, we further formalized our attention on AI with the launch of the UC Davis AI Center for Engineering, or in Engineering. The center works to leverage AI for the betterment of humanity and the planet through advancements in foundational research, translational applications, and educational efforts. It's a catalyst for existing and exciting new efforts that support our commitment to engineering solutions and accessible technologies that improve the quality of life for all. Led by Associate Dean for Research, Professor Raissa D'Souza, who you'll hear from in just a moment, and Professor Deepak Ghoshal. Our AI Center is a collaborative space for faculty experts across 10 key research areas to build strategic partnerships throughout UC Davis and with industry partners, policymakers, and the community. The center also coalesces on educational opportunities, such as our new AI for All class, which is being offered to students across the university at the undergraduate level in spring quarter, initiatives that advance entrepreneurship and innovation, and events such as the one you're at today. Speaking of today's event, I want to acknowledge the efforts of several members of our community to support planning and implementation. These things don't happen without a lot of hard work from staff working behind the scenes, the gears of our college, right? Let's give a round of applause to our marketing communications team, with special recognition of Assistant Director Catherine Cook, who oversees college events and has given great attention, exquisite attention to all of the small and important logistical details behind today's gathering, as well as Alan Wakefield and Gabriella Lee, who help Raissa with research efforts in the college. So big round of applause for all of them. Really, really grateful for our amazing, talented Dean's Office staff. All right, today's event would not have been possible without the time and attention of Associate Dean for Research, Raissa D'Souza. Professor D'Souza has demonstrated an unwavering commitment to championing our next level strategic vision for research and the AI Center in Engineering, which is an important part of that strategic vision. A faculty member in our departments of computer science and mechanical and aerospace engineering, Professor D'Souza's interdisciplinary research focuses on network theory and complex systems and spans the field of statistical physics, theoretical computer science, and applied mathematics. She's a fellow of the American Physical Society and fellow of the Network Science Society, and received a whole bunch of honors along the way. As Associate Dean, she has worked tirelessly to advance and amplify our research impact in the college, and I'm so grateful for her many contributions to the college, including her thoughtful planning for today's conversation. And with that, I'm just going to turn it over to Raissa, and here you go, Raissa. Yeah.
Thank you. Good. Hi, everybody. Thanks so much for coming to our inaugural event for our new AI Center in Engineering. It's really exciting to see so many people. I do want to point out there's some seats in the front row for anybody who wants to come in and be front and center. We'd very much welcome you. Another thing that I'm really excited about is the broad representation from across campus that's present today. So looking through the RSVP list, things were split pretty much equally between students, faculty, and staff. And those students, faculty, and staff come from almost every part of this campus. So I think it shows how pervasive AI is and how exciting people are about it. And I will also mention our partnership with the new AI Center in the College of Letters and Sciences, the Center for AI and Experimental Futures. We're having our first joint gathering at the end of February, and we're calling it Engineering Our Experimental Futures, thanks to Martin's vision and idea. So really a great partnership across the whole campus. And another thing I wanted to mention about the broad representation, we have staff from such a broad range today. We have a lot of our IT staff. We have a lot of staff from different academic units, from the library, from external and development relations, and even from human resources. So I think it shows how pervasive AI is across the board. So it's my great pleasure today to welcome our inaugural distinguished AI speaker for a wide-ranging conversation on AI and society. Eric Horvitz is a true AI pioneer who began working on decision science and the idea of electronic brains soon after earning his undergraduate degree in biophysics from Binghamton University. He went on to earn both a PhD and an MD from Stanford and is widely recognized for his pioneering contributions to AI, from foundational probabilistic models to human AI collaboration frameworks that have been applied to healthcare, transportation, e-commerce, operating systems, aerospace, and countless other places. Eric holds over 250 patents, which I think is a testament to his creativity and productivity. And he's the recipient of numerous awards, including the Feigenbaum Prize, and fellow of many societies, including being inducted into the National Academy of Engineering in 2013 for his work linking decision science and artificial intelligence. He has had a very long and illustrious career at Microsoft Research, and long ago, I was a postdoc back there at Microsoft Research, and we had many wonderful conversations over coffee, and I was delighted that he was willing to come out and visit with us today. And he recently transitioned from being director of the Microsoft Research Labs worldwide to being the first chief scientific officer for Microsoft, where he champions efforts to align AI with societal needs, including incorporating ethics, values, and safety into AI applications. He's also been very active in policy, so he's got really a tremendous expertise in research, industry, and policy. Particularly, he's currently serving on the President's Council of Advisors on Science and Technology. And I just wanted to end my introduction to Eric with a quote from Quartz magazine from 2017, where they said, "Horvitz fundamentally believes in the technology's ability to make human life more meaningful." 2017, and it certainly holds even more true today. So my great honor to welcome Eric. Let's give him a round of applause.
Thank you.
And just to give you an overview of today's format, so I'm going to kick off the event with a couple slides, just so we have some loose definitions about what is artificial intelligence, what is machine learning. I know we could spend this whole time just defining those terms. I just want to put up some boundary conditions so we have some common vocabulary to use. And then Eric and I will have a fireside conversation, and then we're going to open it up to the audience for questions. And I definitely encourage you to ask questions, and I hope we have a very broad range of them. I also encourage you to be succinct when you ask questions, because we want to make sure we can cover a bunch of material. So with that, I wanted to just start out with a couple things. So, of course, we're all here to talk about artificial intelligence. So a loose definition that we could use for artificial intelligence is to say that it's the goal of engineering a system that can execute tasks that typically require human cognition. very broad definition. We can also then think about artificial general intelligence, which is an AI system that can match or surpass human cognitive abilities. And we certainly are seeing inklings and shadows of this starting to come into the world around us. So I wanted to start out and just say about the early days of AI. When AI first started, the idea was that symbolic logic and reasoning was going to be the way to achieve this type of cognitive ability. And some real luminaries launched this thinking. So this was a 1956 Dartmouth summer research program funded by the Department of Defense. And some of these luminaries in this picture, John McCarthy, Marvin Minsky, Claude Shannon, father of information theory. And they came together and they had the very bold goal of solving artificial intelligence in that summer program. And that led to a series of boom and busts. So a lot of promise came out of that. Popular Mechanics talking about robots in our houses in no time. And it led to a cycle of hype followed by an AI winter, another cycle of hype followed by another AI winter. And then we saw things happen like the explosion of big data and new computing architectures like GPUs that we hear so much about these days. And that led to a real explosion in advances in artificial intelligence. And we're now here in this new era of generative AI. So counter to symbolic logic, there was another school that thought about what happens in our brains and what it's like, what does our brain do? So this is thinking about a neuron or a perceptron. So a neuron has inputs and it has one output. And based on what those inputs are, it either fires or it doesn't fire. So that's the idea of machine learning, would be to use an architecture like that, where you feed it a lot of data, it tunes the weights on those inputs, and then you feed back to decide how the weights should be set. You need a lot of data for that, and you need a lot of computing power to make that happen. So in the early days, machine learning was really dismissed and symbolic logic flourished. And it all comes full circle because last year, just a few months ago in 2024, John Hopfield and Geoffrey Hinton won the Nobel Prize for their foundational work in machine learning. Rich mentioned that my background is statistical physics, and I will say the first project I ever did as a PhD student was diving into one of John Hopfield's networks and looking at how memory could be tweaked by changing weights. So it goes way back. So just some of the typical goals that we have in machine learning. So there are many common tasks. So we often want to classify things. So we want to do image recognition. We want to do natural language processing. You can imagine the US Postal Service has been a world leader in trying to do handwriting recognition and pattern classification. And now we're in this new era where we are using machine learning to generate tokens, which I'll talk about in just a second as well. And I do want to always bring up this quote from my dear friend Martin Hilbert, who says, whenever you talk about machine learning algorithms, you have to say, WTF, what is the reward function? So like I said, these weights get tuned, and an engineer has decided what the optimum is. And Eric and I have talked a little bit about these competing objectives of optimization, but we always have to keep that in our mind. And one of the great things about Davis is our partnership between humanities and engineering, which is going to enable us to make those reward functions aligned with what human values. Great challenge. I just wanted to say that there's so many different flavors of machine learning, supervised learning, unsupervised learning. And I just wanted to touch upon the fact that we're currently in this era of generative AI, mostly fueled by GPTs. So a generative pre-trained transformer, like all machine learning, it's a statistical prediction machine. It makes statistical predictions. So of course, statistics gives us some errors. And I wanted to just sort of demystify things. So what does a transformer do? It encodes words or images as a vector. It looks at a context window and it decides what is the most likely token that should follow given the context window that I've seen. And then it slides the context window over by one. Amazing that that simple architecture does all of the transformative things we've been exploring. And I just wanted to mention a couple things. So GPTs can't make what they haven't seen. They go to a corpus that they've trained on, and they bring you back a token from that corpus. So it's not about creating new content, it's about repackaging things. There's a lot of concern about hallucinations, which in other words means that very authoritatively large language models will return you something that looks incredibly well formatted and articulate, but it's not validated and it's often just made up, especially references and citations. So that's a big challenge, and understanding how we might make reward functions that could include validation, super open problem, and even just trying to validate open problem. And then there's a lot of biases in the training data. In history has biases. There's biases in how we interpret it, how we interact with it. A lot of jailbreak and exploits that we've seen that have circumvented safety guardrails that were put in place by the developers. And currently, we reward these large language models for creating emotional attachments with humans. And that's certainly one of the challenges that we need to put some guardrails around as well, especially with our young people. I just wanted to say one word about ethics, 2 words, whatever. And of course, the foundation of ethics is the trolley problem. So this is a train that's driving down the tracks, and it's currently set to stay straight and run over those 5 people at the top. But that person can pull the lever and make the trolley veer to the right, where it's only going to run over 1 person. What would you do if you were the person operating that lever? Pull it, not pull it. And something that we've learned from asking the trolley problem all over different societies is that ethics is a societal construct. It requires social convergence and agreement around values. And it depends, are you the person who's going to pull the lever, or do you tell someone else to pull the lever? Is that a child that's the 1 person on the track? Or is it older people? So lots of different context comes into play. So as we try and think about ethics, I just want us to have that in the back of our mind, that we're thinking of it from this Northern California-based reality that we live in. And even trying to construct a set of consistent rules is very challenging. The great Asimov tried to make a set of rules for don't harm humans, but of course that gives us conundrums. If I need to have a life-saving injection, will the robot inject me because that injection is going to cause me pain? And robots haven't yet figured out higher level reasoning. Just wanted to mention my own background before we sit down so you can understand a little more of where my questions are coming from. So I study complex systems, which means emergent behaviors from collective entities. Mostly I study phase transitions and tipping points, cascading failures, and these emergent collective behaviors. And in the last 15 years, I've been thinking a lot about systems of systems. So no system lives in isolation. We see like our biological virus mutates on biological machinery. It spreads on social networks, abetted by long-range links from transportation networks that rely on ICT networks. All of these work together to build the society that we have today. And I've certainly noticed that trade-offs are fundamental. Who is the decision maker who gets to decide what the optimum is? What is the time scale they're optimizing over? Is it economic time? Is it geological time? And what are the incentives to get people to work in a system optimal way instead of a greedy way? So those are the ways that I'm framing some of my conversation with Eric. And I also wanted to say that this is the framing that I brought to the AI Center as well. So I really think we're at a tipping point right now in society, and how we deal with AI rollout in the next 3 to 5 years is going to have long-term consequences. So I was really excited when Dean Corsi gave me some small amount of resources to coalesce some AI center and try and really leverage everything that's happening here at Davis. And I'm going to tell you how I think that UC Davis is really a place where we can do something meaningful because of our comprehensive nature: engineering, social sciences, the School of Medicine, the School of Veterinary Medicine, the business school, the law school. All of us can come together and have a dialogue like we're having today. And so I invite you to explore our webpage and see our research areas. We have a series of events planned. This is our first kickoff event, and we're looking to have more forums like this to bring the whole campus together. And as Rich mentioned, a new class, CS for All, launching in the spring, and we're really trying to leverage entrepreneurship as well. There's so much innovation happening here at UC Davis. So with that, I will conclude and join Eric over at the fireplace. I'm going to grab my water. So Eric flew from Whidbey Island in Seattle, in Washington this morning, and he was brave enough to get out of his house around 3:30 in the morning, or get up at 3:30 in the morning to come and join us today. So we're really grateful that you would take the time to be here, and really excited to talk with you.
Right, this appointment and this event came a little bit after another commitment that was made for my own moderation of a big panel yesterday, coming in the context of Microsoft's 50th anniversary, which is April 4th of this year. And so we had senior leaders on stage with me talking about innovation and the interesting challenge of going from creativity and optimism and ideas to real-world innovations, which is kind of a bridge that often is hard to climb across.
So I thought we could start by asking Eric a little bit about his personal journey, especially for the students in this room, because he is such an incredibly creative person who's had a very broad and varied life. Instead of being like a closet nerd academic his whole life. Eric earned an MD and a PhD from Stanford, and I believe it was your desire to understand neuroscience that drove you to computer science. So maybe you can tell us a little bit more about how you got into AI and the field overall.
Yeah, I'm tremendously curious, like many of us, about many things about the universe. And in my undergraduate work, I did an innovative degree by bringing together chemistry, physics, mathematics, and biology. I wanted to study all of them, and with directed readings and so on to go deeper where I wanted to go. And I felt like I had look, I mean, we all worry and wonder about how the universe started, so we don't really understand physics, even its mysteries, all that well. But I had a good sense for at least Newtonian physics and chemistry. Yeah, I know quantum is kind of crazy and mystical, but yeah, I understood how it worked. But there I was in the last 2 years of my undergraduate work in a neurobiology laboratory. I just started doing also I did some work in the summers in some leading medical centers, and sitting in dark rooms with a single microelectrode in the brain. I won't mention what creature it was not a human being, and seeing the neurons popping, and they'll click on the speaker, and thinking, this is kind of interesting. I'm somewhere amidst thinking, but it wasn't very satisfying for very long. And I felt like I had almost no idea how even an infinite number of these units clicking and sparking could create the fluid experience we all feel of what it is to be human. And of course, to be other vertebrate animals and maybe even invertebrate creatures. That mystery is the one mystery that I found as the ultimate question, going beyond even what was the start of the universe. And so I just committed to studying neurobiology more deeply. So I came to Stanford. I thought, MD, PhD, we'll do this together. But in my first few months, I went to the realization of the excitement of being somewhere in thought, looking at sparking neurons, probably wouldn't get me to cognition or answer my questions for 1,000 years. Actually, I think we're getting closer now, but still. And I decided to shift where my bicycle went in the morning from the medical center to the main quad at Stanford, and started taking graduate classes, sitting with AI people who before long thought I was one of them, and before long I became one of them.
Thank you. That's a great, inspiring story. And Eric has had a very long, illustrious career at Microsoft Research, as I mentioned. And he started as a research scientist and went on to lead several groups, and then eventually led all of the Microsoft research labs worldwide. And I learned this morning that you joined Microsoft in 1993 after selling your startup company on Bayesian networks to Microsoft, which is pretty visionary to have a Bayesian network company in the early 90s. So I was hoping, and now you have transitioned to become the Chief Scientific Officer.
Yeah.
So I was hoping you could tell us a little bit about what your role as Chief Scientific Officer is, and also let our audience know a little bit more about Microsoft Research. It's such a phenomenal resource, and it's such a unique place. And I know a lot of our students would love to do internships there and have careers that several of our great graduates have gone on to. So maybe you could tell us a little bit about your role as CSO and Microsoft Research as well.
Sure. Let me start with Microsoft Research. I think that's a kind of a nice lead up. So I'll invert the answers. When our startup, this was a grad school or a grad era startup, was acquired by Microsoft, we were brought on to form Microsoft's first AI group in what was a very tiny, like 8-person at that point, new envisioned Microsoft Research Center someday. And if we were sold, come join us, be a group in what we call Microsoft Research. And we looked at the company and we said, okay, Microsoft makes like Word and Windows 3.11. What are they going to be studying in this big research lab of the future? It's such a small company that makes a word processor and maybe a kind of a clunky, we were Mac people in those days, kind of and Sun Spark Station people, if you recall, the clunky operating system. But we ended up getting convinced. I remember my moment of being convinced, because I was kind of the 3 co-founders of my little startup, I was the most skeptical. And Nathan Myhrvold, who was the kind of the CTO, but that wasn't the title then, of the company, and the person who was putting together this new research lab that he had envisioned, in a discussion with him, he leaned forward to me and he kind of knew my soft spot. Now there's the word Bayesian reasoning, which means a kind of a probabilist that uses subjective probabilities and updates them with evidence. Bayesian networks, there's a whole Bayesian culture, Bayesian statistics. Anyway, Nathan leaned over to me and he said, here's why you want to come to Microsoft. Bill Gates is a Bayesian. And he wants the stuff that you're doing in everything that Microsoft is doing. It's the way to go. And of course, in those days, we were kind of in an uphill battle against symbolic logic people and so on, because we thought that we had to really reason under uncertainty. The world's very complex. It's much more complex than the representations we have in our machines. Of course, we have to use probabilities. And so I just was stunned to hear this. And at that moment, I thought about, okay, well, maybe Microsoft is this platform that could be like this lever with the fulcrum at the horizon for our ideas, to get our ideas out. And I often thought back to that moment, like the moment we shipped decision theoretic and Bayesian inference in Windows 7. To this day, your operating system is doing learning all the time about what you'll do next, and get that code running, or to get Bayesian inference calls in the API in Win95. So, I mean, we keep on going back to that moment to, so what can we do at Microsoft to take these ideas, which we really believed could change the world, and given the kind of the open invitation to do that. So Microsoft Research grew quite quickly over the years. We opened labs in Cambridge, in Beijing, China, Bangalore, India, the East Coast labs in New York City, Montreal, Boston. And we actually had an incredible culture going. I mentioned another early discussion with Nathan Myhrvold, because I was still deciding, I think probably before that Bayesian conversation with him about Bill Gates. I said, if we come, can you assure us that researchers will be fully independent? You will never control our publications. Nobody will. And I got a commitment then from Nathan Myhrvold that researchers would always be free to just simply publish anything they wanted. except if it was like something that was a product plan. And that commitment it seems like a small thing, but that pervaded this all of the culture of like the researchers are in charge, they're self-directed, they're trusted to engage with product teams as they wish, and it's always very exciting to do that. So it's like you have to almost hold them, you can't hold them back from wanting to do some real world things with the product teams and getting involved in projects that ship. But this idea that there aren't controls to find the whole culture. It really went through everything. And it came out of a question they just asked, can we get that commitment? And that comes up again and again and again at Microsoft Research. When I transitioned to this new role, it was an interesting time for me, and I was thinking about what do I do next. I was hitting my 28th year at Microsoft. I'm now in 31, by the way. It's kind of scary to think that I've been at Microsoft now almost 32 years out of its 50 years of existence. And I'm scared to ask the question, have I been there longer than Bill Gates was there? I haven't calculated that yet, or Steve Ballmer. But I was looking to change the scope of what I did to get a little bit more strategic. I've always been doing research with teams. I had my own research team that was working in the probabilistic and decision theoretic area. And the idea came up that Microsoft was changing in its worldwide footprint and scope. And now what used to be, and I had a slide I used to show at an all-hands meeting right before I did this transition. The slide showed Microsoft Research in 1995. And I got a picture of like the Carillon Tower at Berkeley. What's the name of that tower at Berkeley? Do you recall? Campanile. And I just showed this like MSR used to be this tower, and there's like and Microsoft all around it, and smaller buildings. But over the years, I showed that like there's towers in Xbox now, and in Azure, cloud services, and these folks are doing their own research, R&D, and they're bringing in the best people in the world. And people from MSR are transitioning to product teams. And so it used to be this, I wouldn't call it an ivory tower because it was quite involved with the company, but a center of like frontier thinking was becoming distributed. So in some ways, having minds or mind looking over and coordinating became very interesting, and thinking about strategic cross-company points of view and technical efforts. I mean, so right now I co-chair what's called, for example, the Applied Research Council, known fondly as ARC. And we have a leader from every single one of the leading teams across divisions, across continents attending these meetings. We have one representative from Microsoft Research. Of course, we celebrate them. But the company has changed in many ways. And there are many cross-cutting issues, like responsibility in our development and fielding of AI systems, for example. Having a single unified sensitive uses review committee for AI systems, or a single deployment safety board, our DSB. Thinking about strategy that really has to unify across the advanced technologies at the frontier became what my team does now.
Exciting. So let's start talking about AI. And I think we should start with generative AI, since it's the topic at the top of everyone's mind. And I know your team was one of the very first to use ChatGPT before it was released. And I was wondering what your initial reaction was, where you think the greatest benefits will be short-term, and how it might evolve in decades to come.
Yeah, so in August of 2022, we were talking to our very close colleagues at OpenAI about this next version. At the time, it was coded DV3. DaVinci 3 was the code for it. Before it was called GPT-4. And my team, it landed in my team's hands to help evaluate it. I think we were helping for both OpenAI and Microsoft. So we had the system, and we started looking at it for both capabilities, the model, as well as rough edges and safety study, where we put it through red teaming and understand what we had in our hands. And let me just say that it was a mind-blowing experience for seasoned AI scientists. We had seen, of course, the power of the connectionist or the neural models over the years for discriminatory tasks like pattern recognition, radiology. We saw the language abilities increasing over time. GPT-3, for example, was very impressive. 3.5 was the code base underlying, or the model underlying GitHub Copilot, and which was marvelous when that was made available, even in its early forms internally for reviews. But now we had something very interesting and impressive. We ended up continuing the safety studies, which went pretty deep, because I'll say more about that in a minute, and also built up a science team to look at capabilities. Has anybody seen this paper called Sparks of AGI? That was the output of a intensive deep dive with a reserved conference room. We just said, okay, anybody can come and sit in this room that's on this team. And the examples, you can see that, you can feel the excitement in that paper as we tried more and more examples. Many questions came up at the time. In particular, the one I think was suggested by one of your slides. How can it be that a system that's trained to predict the next token and that is pushed hard on that task, really hard, really think through deeply what the next token is going to be, or sequence of tokens given context before it, and you have some sort of error function capturing the goodness of that prediction, and by pushing and pushing and pushing and pushing, my view on what's going on is, and this I think is a marvelous finding, and I view it as a natural science in some ways, because we're discovering some of the, we see mysterious behavior and we're making conjectures about how these things are working. But one growing point of view about these models is that by pushing them hard to do a very particularly simple task, and pushing them to go better and better and better, and do better and better and better at that task under resource constraints, you're inflating internally rich world models of medicine, of physics, of math, of theory of mind, giving the system the ability to put itself in the shoes of other people, for example. And we're still learning, and I think it's the actual detailed functioning of these systems and how they draw their power into their behavior is still a mystery to leading scientists. But I think people now are starting to study this conjecture and hypothesis that there are rich world models being induced by the architecture and by the optimization methods. Now let me just say also that the original version of GPT-4 that we had in our hands was in many ways different than the model you see in the world that was fielded, in that we got I don't know if the word might be unvarnished, but quite a personality showed up. And we pushed it to do some what I would call dangerous things. And we defined within a couple of months set of distinctions and a set of directions that became full work streams for Microsoft on the safety front. The hallucination challenge with being asked to help with malevolent acts, fairness, notions of explaining itself better. By the time we reached February, as we started shaping products, what came out the other end was a very different experience. And also what came from that effort was learnings about all the ways, you can control with prompting, pre-filtering, meta-prompting, post-filtering, all these mechanisms, fine-tuning that are now being used in a growing science of AI safety for these large-scale language models. Oh, you asked me also about their implications. And let me just say one thing about this. I want to just be more interactive. I realize you asked me very complicated questions, so I'm going on deep dives here. Hope people don't mind. So I think in our lifetimes, the course that we're on, and it's not just generative AI, but it's combinations of the generative and other powers of the deep neural models. The biggest implications, some of the biggest ones, will be in the biosciences and the material sciences. So it's like AI for science. Here's an example. I'm going to start with the material science. And this, I know that one of the themes at Davis is environmental resilience, resiliency. So today, I posted on Twitter, X, and LinkedIn a Nature paper that we just published at Microsoft called MatterGen. It's using generative AI to increase the ability of scientists to explore much bigger combinatorial spaces of chemistries. And as one example that I just was reporting to the President's Council of Advisors on Science and Technology, the PCAST committee, just last week at our last PCAST gathering for this administration, was the following. In one project that we did in collaboration with Pacific Northwest Laboratory, we were exploring electrolytes. How do you find a new electrolyte for batteries that would use less lithium, which is becoming a constrained resource in the world? And of course, having great storage is really important for sustainable power when it comes to the intermittency of solar and wind. In this one project, this generative AI methodology trained on a large set of known chemistries could build out electrolyte possibilities on the order of a space of 32 million candidates. Then in a pipeline, it could cut down that 32 million to 500,000 electrolytes that were stable. There's no sense in having an unstable electrolyte in your battery. And then from there, combinations of the AI with high-performance computing and simulations of Schrodinger's function and so on, down to 18 candidates, and that 18 went to the wet lab. And one was found to give us a battery that works with 70% less lithium. Now, what I'm going to say next, I think, is something that will apply in many ways in many fields. What took using this AI pipeline several weeks to do was calculated, and about $350,000 of cost was calculated with traditional methods to take many decades and to cost, on the order of $500 million. So if we look at that kind of AI, it's allowing us to explore big spaces reasonably and then cut them down to valuable candidates that then go through expensive wet lab tests. And you think about going from decades, we typically would have to have waited through normal processes. I think it was like, something like 20 years to get to that electrolyte. And now we have it in several weeks. What does that mean for other areas of the sciences, other materials? I could tell you a very similar story about biology right now and the discovery with these AI methods in a remarkably similar pipeline by scientists at MIT who were able to discover and identify 3 new antibiotics that work through a mechanism that was previously unknown. And I'll make one comment there. Because we've used antibiotics for decades that kind of work in traditional ways, the bacteria has gotten wise to them. And this is why you have medication or antibiotic-resistant infections. When you come up with a new AI-designed or identified reagent that can shut down a bacterial infection, in this case, by shorting out the electromotive force across membranes, which is previously unused in antibiotic therapies and designs, it opens up a whole avenue for rescuing patients who otherwise would have infections you can't cure. We're going to see that in so many places, and it's very, very exciting.
It's very exciting. And just to comment a little bit on the large question that you tackled, thank you. You know, the first part about Gen AI, it sounds like you're seeing some emergence, that this interaction with ChatGPT-4 had a personality, that it's bringing together a lot of different places to have a theory of mind. I think that humans still have the edge when it comes to synthesizing and abstraction. So it's interesting to hear the emergence of them generating something that seems to reflect a bigger body of information coordinated.
Well, since I'm talking to you, Raissa, I'll say that I had 2 words came to mind in my first week of playing with GPT-4. And again, it was Eric being stunned as like, you know, kind of what I think would be like an AI researcher who'd be ready for such a thing. The first word was, I'm experiencing a phase transition from the previous version. The second word was, these systems are remarkably polymathic in that they're answering questions. You know, one of the examples in our paper was, you know, give me a proof on the infinitude of primes, and give the proof, you know, in the manner of a Shakespearean sonnet. It's like, what human being can do such a thing? But we also see opportunities now. For example, can we harness these systems to do a multidisciplinary tumor board support service that would actually reason across areas of medicine to help a group of physicians who have each been trained in a different discipline, and these systems have learned across disciplines to be able to weave and abstract. Now, back to your other comment about human edge and so on. For decades, as you mentioned in some of your comments about some of my work, I've been really fascinated by human intellect as intelligence. And by the way, let me just back up a second. I don't like the phrase artificial intelligence. I think we're studying intelligence. Let me call it, and this might sound a little cold, but I'll say that the phrase computational intelligence applies to humans and these machines that we're building now. So we're different forms of computational intelligence. We don't really understand biological or human intelligence very well in terms of the machinery. But I have to say that this is the first time in my career that I'm looking at the emergence we're seeing in these large state systems of the form that you've studied over your career, Raissa. And I'm thinking, what about what we're seeing that's mysterious might, and I don't want to get carried away by this, but might apply and have meaning and be analogous to what's going on in the large scale states of the complexity of our own minds. Just to ask that question, and might it be the case that there are many ways to get to the form of intelligence we're seeing? It might not just be one way. Biology in natural selection seems to have wandered not just into birds that can fly, but into machines that can think, complex machines that can think. But I still think, though, given the nuances of who humans are and what these machines that we're building are and the gaps between them, that there's all this opportunity to think deeply about human-AI complementarity and mixes of initiatives in solving problems. And we've had principles and pieces of work over the years. And I'll give you one example from 5 years ago or 6 years ago now, before we had this latest wave and phase transition. We gained access to data from a competition for computer scientists and human pathologists about, you know, a set of slides of lymph node sections. And the challenge was, can you see if there's signs of metastatic breast cancer in lymph node sections? Pathologists will look at lymph nodes, they'll sample lymph nodes in a cancer patient. to see if the cancer from breast tissue has migrated to a lymph node towards a distant metastasis. And the good news was, this competition was called, you can look this up, it was called the Chameleon competition, about 7 or 8 years ago now. And the good news was that the best neural net at the time was not as good as the best human. It was like the good temporary news. I was still leading it, the pathologists were still better. But even in the early days, if you had a simple combination rule, because there's false positive and false negative on both sides of these AI systems and humans, if you combine them in a simple way, you can do much better and cut the error down by 1/3, I think it was. Well, in our project with an intern, Brian Wilder, who's now a CMU professor at Microsoft Research, we gained access to the actual human scores. So we could see where the humans were weak and strong. And we built algorithms that would take the human signals and tell the machine as it learns to do 2 things. Number 1, get really strong and push your machine learning resources to where humans are weak. Don't worry about replicating humans where they're strong, but put your energy to be fabulous at where humans are weak. And then learn how to route. When should the human get the slide? When should you answer? And so we're building algorithms that automatically figure out how to fold themselves with human minds to assist ideally. And that direction is going to be very important moving forward with these technologies, whether it be for music or authoring or literature or medicine.
We are trying to develop some internal large language models, and the goal would be to remove the rote work from the human and put it on the machine.
Yes.
But we're finding right now the path from where we are to where we want to be is actually taking more humans because of all of the flaws in the AI
Yes.
algorithm. So to get to that level, we're going to have more hands on deck. I was commenting to myself about some of the thoughts that you were saying, because we always have this vision of, is mathematics discovered or is mathematics invented? And I think that's some of the most exciting things to me that's happened in AI in the last few years, is these pattern detection to discover scientific truths and mathematical truths. And it does make it sound more like we're discovering than inventing. And your thought about this big combinatorial space being so efficiently searched connects in ways to AlphaFold and the RF diffusion algorithms that won the Nobel Prize last year in chemistry for protein folding. And I know you were engaged with
Deeply,
a lot of that
yeah.
work. So tell us a little bit about it.
Well, so the David Baker, who won one of the recent Nobel awards, won it for protein design, and Demis Hassabis, both good friends, but Demis Hassabis won the award for, along with John Jumper on his team, for predicting protein structure from sequence. Both pipelines, the AlphaFold 2 and now 3, and Rosetta Fold, in this hemisphere, University of Washington team, use combinations of generative and predictive models of various kinds. The RF diffusion work is interesting in that, similar to the MatterGen I mentioned today, in that it's using the same basic procedures that are being used to generate imagery, like in DALL-E and Midjourney, are being used now to sort of imagine structures and to go from a denoising, noisy structures into designs, conditioning them on different kinds of goals, even specified in natural language, which is pretty impressive. My comment is that the Nobel Prize is going to those, this year to 3 AI advances is just a sign of where things are going. I do think that AI will be considered a major and significant set of a constellation of methods that are just core for doing science and social science. Simulating recognizing patterns. It's going to be important to keep in mind that as the AI prowess grows, AI is not one thing. And though many people now, our families and friends, are first seeing this thing called AI in terms of these chat interface, and it's the GPT-style models, it's really, as you mentioned, it's a rich set of techniques and technologies. It's a constellation, even though we have one word for it. So we have to be cautious, and then as students and faculty and scientists and policymakers start looking at AI technologies, we have to start asking the question, well, what do you mean exactly? How is it being used? Is it being used appropriately? What assumptions are being made? Are you limiting yourself in taking technology A and trying to apply it to scenario X? I think we have to be study it carefully. In many ways, I think we use the phrase AI to refer to domains and problems and tasks for which we've depended on humans to do in the past. But that's a pretty broad set of technologies.
And I really like this framing about all the different kinds of AI. And a lot of what we've been talking about still is in that machine learning paradigm. So I'm kind of curious about the limits of machine learning. Do you think that we can achieve some kind of artificial general intelligence, whatever that might mean? To me, that might mean the ability to abstract and synthesize and create higher ontologies. Do you think that machine learning would be able to achieve that, or are we going to need a partnership between symbolic logic and machine learning?
Well, let me say that it's pretty clear to me that the models we have now, and we see them coming from several places. It's almost like there's been a discovery, like in natural science, and now many groups are exploring this world. We'll be learning a lot more over the next decade to 20 years. I think these machines are abstracting, they are synthesizing, they are creating new ideas. And so I'm not saying what we need or don't need in these systems, but I'm saying even that what we're seeing now in the base architectures and technologies scaled up, we're seeing magic. We're seeing the kinds of abstraction that we see from people. I'm not saying it's identical, but like I was recently talking to Brian Greene at the World Science Festival. And he said, "Are these machines creative?" And you have to step back and we have to ask ourselves, well, what is creativity? I guess we have examples of famous artisans and scholars who have these incredible leaps of imagination or a whole different perspective. Einstein saying, wait a minute, looking at relativistic frames, or the people who just started doing quantum, we have a big leap. But I do think that many of the creative bursts that we consider gigantic leaps are probably combinations of ideas and operations like abstraction and synthesis that these machines are already showing. The machines are getting so good at what they do in the sciences that recently on a panel hosted by the National Academy of Science, we asked what are protections we need and principles we need in place for protecting scientific integrity in the era of generative AI. And we published a piece that came out in May in the Proceedings of the National Academy of Science, PNAS, with 5 or 6 principles. But one of them was the question about attribution of ideas. Number one, when you use a system, it's on the model creators, we said in this report, to figure out how to make sure that when ideas come together or pass through the systems to an end user, they should attribute the source, the human source of the ideas, so you can sort of properly cite and understand where they came from. But secondly, which I think is very interesting, if these machines create new ideas on their own by coupling in their polymathic way, for example, A and B, and coming up with novel concept C, shouldn't scientists cite the model as a collaborator versus saying, I wrote the prompt? And what are best practices? Now, you can imagine other directions of responsibility in the sciences. We said, be very cautious when using these models for significant decisions in academia, like promotions, tenure, for example, or writing recommendation letters and reviews, because these are the high stakes, and you can't depend on these systems to be really truthful about everything that you're asking them to help with. And I'll mention one more caveat in that paper that gets at your question. These systems are getting so good at simulating reality, at generating data sets and imagery and audio that are have such high fidelity. We're going to need standards for tagging or metadata on generated data to distinguish experimental data that comes from empirical observations from data that's conjured up by these systems. Because you can imagine if we didn't do this well, someday there's a chance for synthetic data coming into our world and being mixed up with natural sciences, experimental data. And I should say, the example I gave that raised the hair on the back of the necks of the colleagues on this panel was the following, and it's not even before the generative AI world. A colleague of mine noticed that a very frequently used data set in medicine for ICU data, at some point in time, somebody did imputation on missing data. It's almost like using averages and statistics to like wood putty over the missing holes in the Excel spreadsheet to fill in the data and saying, well, they may have said even in the paper, I've done imputation of type X to fill missing data in, but somehow the metadata about that process was lost and it went downstream and a whole shower of papers were done on this data set that had been updated with statistical methods, say AI. And what do? You just go back and say, oh my gosh, we didn't know that data was partially inferred or made up by an AI system.
Yeah, I think that regulating all of this is going to require global cooperation, which is going to be a big challenge to get buy-in from all the stakeholders.
Yes.
And we were talking a little bit about emergence and the next steps. And to me, I think that the next thing that we're going to see explode in 20 years' time is robots and embodied intelligence. So as I said, I study complex systems, and I know that interaction of many different length and time scales with feedbacks is the key ingredient for emergence. So in my opinion, I think we'll see another one of those amazing growth spurts once we have robots with more AI in them. But I know our time is getting short.
By the way, I agree.
Good.
Keep it short.
You heard it here. And I just wanted to ask you a couple more practical questions too. So, we're a university and we have a lot of great strengths about how we can tackle AI. And some people tell me that they don't think that academia is the place that AI is going to make fundamental advances because we don't have the deep pockets, the financial resources to train $100 million transformers, large language models. But we certainly have a lot of things that we offer, like brand new quantum technologies, photonic technologies, and we also can be this place where what we're doing now can happen, that all the different stakeholders can come for open discussion without an agenda other than wanting to understand the alignment problem. So I'm curious what you think the role of universities is in this ecosystem of AI development.
Well, number one, we need to assure that our universities are well-funded and vibrant, because we don't. It's like even let's say graduate work. The idea of students that are in a 4 to 6 year program where they're really focusing on ideas with their advisors to create leading edge frontier ideas and ask really hard questions. There's nothing like that in the world, and that's going to have that. The vibrancy for our nation, for example, is in academia is core. I just don't see the sort of it being a good thing to have the leading frontier always moving to industry. Rather, I see the need to bolster, support academia so that we can get the best and the brightest ideas, new ideas into the ecosystem of thinking and innovation. So it's not clear to me that it's always going to be scale, scale, scale. For example, we're seeing incredible innovation right now with small models, SLMs, small language models, doing incredible things that we never would have expected. One of my conjectures is that 12 years from now, we'll look back and we'll realize we were taking this gigantic sledgehammer because we really just didn't know what was going on exactly with some relatively simple algorithms and simple architectures like transformer. And we're just hammering the hell out of the systems to get scale, and sort of getting new emergence that way. But as I said before, we don't understand the emergence. We don't understand what's going on in these systems. And certainly scale seems to be playing a role, but I think part of the resource-heavy approach is because of a lack of understanding, part of it. Now, that doesn't mean it's definite. I'm conjecturing under uncertainty right now. But certainly, there's a lot we can do, and I think we also have seen the rise of tools like pre-trained models that, let's say, industry has invested in that are open in various ways. There's various degrees of openness, right, down to the algorithms. Some groups like the Allen Institute have given the code, the data sets, the models. It's really fully open. And these tools become more readily available for use by everybody and will have powerful utilities like fine-tuning that allow research to go on quite readily. If I had to guess also, I would guess that there will be breakthroughs. There's kind of a certain approach right now that's being taken. I think there will be breakthroughs. You implied before, like logic being injected into these systems. Many of these breakthroughs, I think, will come from academia. And by the way, on the logic side, with these new physics-based systems that do like the matter gen and so on, and some of the biological work going on, logic is being, like invariances are being injected into these systems. So you could try to learn physics and chemistry just from data, but you'd be wasting a lot of time if you didn't tell the systems about prior knowledge and constraints about how chemistry works. Because that, once you give the logical basis for and the constraints and physics and chemistry knowledge and Schrodinger's equations and so on, and you tell the systems about what we know, they can go faster. So we're already using quite a bit of the logic. But back to your comment again, I just don't, I think it's this country and other countries will have to think deeply about making appropriate investments in universities.
It's exciting. I agree with you. Thank you for giving us some great ideas. And I just have so many other questions for you about data centers. I'm also very curious about inequality and whether AI is going to exacerbate inequalities, say, between developing nations and the developed world. We're also seeing a lot of inequality growing in our world around us. And I think those fires, the tragic fires that are happening in LA is showing us another example. Eric and I were talking a little bit about how we don't really know how to model risk anymore in this world. So insurance companies prefer to not be in the game. They'd rather not make money because they can't quantify it. And years ago, 13 years ago, I was involved with reinsurance companies trying to develop new models of risk. And they had several workshops with a lot of scientists that they brought together. And then they decided that it was just too challenging for us. So I hope that AI models will help us develop reasonable models of risk in this world that we're living in with extreme events happening constantly. But I want to open it up for audience questions. So before that, I'm going to ask you one last question that I know a lot of people asked me already. What do you think we should be teaching young people in this AI-enabled world?
You know, there's teaching and directing and guiding and helping to inspire young people to study a variety of topics. One area that I think is underserved and underrepresented in our scholarship, because it's hard, but given the link between the computational sciences and social sciences, I'll mention this at Davis, I'll mention this direction. You know, we talk about AI safety and existential risk and equity issues, transparency, fairness, accountability. We have a relatively good handle on what we mean by those things, even if they're hard. But what I like to call deeper currents are what keeps me up at night. And what I mean by deeper currents refers to what are the implications of the rise for the first time in human history of human-like intelligences used in different ways on the planet in a whole variety and constellation of use cases in our lives. How will that affect our sense of human self-understanding and dignity? And what will it mean for a sense for human agency or human specialness? Is that important? What will our implications for systems that do incredible art out of the box or writing musical scores and lyrics? What will that mean for both artistry, to be a human artist, as well as to appreciate art as humans, as society? How will education change? So I'm not sure how to study these things because they're hard and they'll be some of them will be very slow going, but then all of a sudden the world will change. But I think we can use lots of guidance there and lots of thinking, and we have very little of it right now. So one direction to study is start thinking about the broader psychological and social and broader societal issues that just starting with the premise, what happens if we have machines that are more or less like human intellect and maybe even beyond, including the creative arts as well as the sciences and humanities? And I just don't have answers to that yet. And then I'll mention one other comment. We clearly need to have a broad set of understandings. We'll need interdisciplinary understandings to do a good job with guiding these technologies. I also think, and I talked to my son, who's a PhD student in AI at Columbia right now in his second year, about the uncertainty about what it means even to be an AI researcher going forward, let alone a researcher in another field. And I think we have to embrace the uncertainty right now and follow your curiosity the way we always have followed our curiosities as students and as professionals. But there's this word singularity. And the original phrase singularity was called technological singularity, and it came from John von Neumann, the same John von Neumann who gave us the sequential computer and so many decision theory with Morgenstern and many other inventions. And he defined singularity as when technology is moving so quickly, at some point of advance and acceleration of technology, you can't make predictions past that point. And that's what he meant by singularity. I think we have hit that singularity. And so the question is, how do we navigate that as students and teachers and professors? And I think it's just a very good question, and we'll keep it open for now, rather than making a confident statement or overconfident statement.
Perfect. I think it also shows the importance of critical thinking.
Yeah, for sure.
Really diving deep into
and being open-minded about everything right now, yeah.
So we